Hello everyone. So today I'm going to talk about pumping lemma for regular languages. So far we have talked about regular languages and have seen different approaches to prove a language is a regular language. So we can create a finite state for that, we can create a DFA, NFA, epsilon NFA, or you can write a regular expression for a language. If you can do any of these, it means that the language is regular and you can prove by just writing a regular expression or creating a finite state automata for the language, you can prove it is regular. Or we can even use the closure properties that we have talked about it in the previous video last week. So today the focus is on the techniques to prove a language is not regular. How we can prove a language is not regular. This is the main focus of this video. In fact, the pumping lemma, the pumping properties that I'm going to talk about is the very useful technique to prove a language is not regular. Before we go further about the pumping lemma, I'm going to just emphasize on one fact. If a language is finite, it is regular. That's enough to prove that a language is regular, because when the language is finite, you can create a finite state automata for that, right? So our focus here is on those languages which are infinite. That's where the question actually will came from. If you have a language which is infinite, so there is a chance that it can be non-regular. We wanted to prove that if that language is non-regular, how to prove it if it is non-regular. So one more point that here I wanted to emphasize is that if you cannot create a finite state for a machine, you have to prove you cannot create a finite state for that. It's not just if I can't create it and say that, okay, I couldn't find a finite state for that. That's not enough. I have to prove that it is not possible to create a finite state for a language. So you will see that it makes it hard to prove a language is not regular. That's why we need this pumping lemma property. So let me show you a couple of examples. The first example here, the set of all binary strings that has n number of zeros followed by n number of ones for any value of n greater than or equal to 0. This language is not regular. This is the one that we have seen in the first lecture that we talked about DFAs and creating finite state machines for regular languages. This is an example of a non-regular language. It is clear that this is, we have proved it using the pigeonhole property, the pigeonhole principle, that this is not regular. But the intuition is that you want to accept all the binary strings of arbitrary length that has n number of zeros and exactly have the same number of ones followed by that. So intuitively it is clear why this is not a regular language, because n is arbitrary, n can be very big, right? As you don't know what is the size of n. So your finite state, if you are going to create a finite state for this language, it should capture all these cases. And basically you need to count all of those zeros so that you can match it by the number of ones at the, which is followed by that. So it is not possible. So intuitively, when you need to count something, it basically comes to mind that this is not regular. The other example here is, if you look at the second example, all the binary strings that have equal number of zeros and ones. Again, this is an example of a non-regular language. when you see a zero, you have to actually keep it and know that, okay, so far how many zeros I have seen, how many ones I have seen, and based on that, accept all the strings that have equal number of zeros and ones. This is also a very well known actually example of a non-regular language, and we can prove it even using the closure properties. We can prove that this is not a regular language. So let's look at the third one. So in the previous two examples, the intuition was that both of these two examples are non-regular, and the reason was that we could not keep counting the numbers because we have finite number of states, and we cannot, because of that, we cannot count arbitrary numbers for the both of the previous two examples. How about the third one? Third one is talking about a language of all binary strings that has equal number of occurrences of this pattern 0, 1 and the pattern 1, 0. So if I'm going to go with the same intuition as I had for the previous two examples, you probably would say that this is not a regular language as well. But yeah, wrong. This is a regular language. We can simply create a DFA for to accept this regular language. If I wanted to show you the DFA, let me see that I think I have created a DFA for that. This is the DFA for the language that covers and that has the equal number of patterns 0, 1 and 1, 0. I'm not going to explain this DFA. If you had any question, you can actually go through it offline, but and if you had any question, actually come back to me. So I just wanted to show you that that intuition can easily go wrong. So if we want to prove something is non-regular, we need a technique, we need an actual proof that the language is not regular. So today we are going to talk about a specific property that all the regular languages have, that specific property, and if we can show a language doesn't have that property, then that's enough to prove that the language is not regular. So I'm going to talk about that property. So let's first see some examples. Look at this finite state machine, finite automata that we have. The question that I have for you is, what is the longest string that can be generated by this finite automaton? So as you can see, we have a couple of loops here over our finite automaton. One loop here, one loop here, and another loop here, right? And because of these loops, actually this language is going to accept, this finite automaton is going to accept strings of infinite length. So for example, you can have as many number of ones as you want here, and then having a 0 going to Q2 is the string is going to be in the language. Or then after that, you can actually iterate over this loop as many times as you want, or you can iterate over this loop as many times as you want. So this finite automaton is going to accept strings of infinite length, right? And therefore, the number of strings that you have in this language is going to be infinite. But the language is definitely regular, right? Because it can be created, it can be represented using this finite automaton. So let me show you a couple of other examples, and using these examples, I wanted to introduced some property for the regular languages which are infinite. So look at this example here. As you can see, the example is in the language. 0, then you have a 0 here, and with another one you come back to an accepting state, right? So over this example that I have, as you can see, this string will actually cover a loop in the finite automaton when you run it over this finite automaton, right? And because of that, that part that we actually covered in a loop here can be, in fact, iterated as many times as we want. This property is called pumping. I have found a part of this string in the language that I can iterate over it, and I can actually pump it, repeat it as many times as I want, and still the strings that will be generated are going to be in the language. And notice that I write here as a I put a star operator over this part, so it means that I can repeat even 0 times. Okay, so it means that even if you repeat 0 times, the resulting is going to be in the language. So a string like 0 is going to be in the language, right? From Q1 it goes to Q2 and it is in the language. So let's look at another example here. 1 1 1 1 1 and 0. Again, this in this string, which is in the language, of course, because it actually iterates over this loop here as many times as you want, and by a 0 you go to Q2. Because this string is covering a loop in the DFA, right, I can iterate over this loop as many times as I want and then go to the accepting state. So it means that I can actually take this part, for example, this part, and say that if I repeat this part of the string, still all the resulting strings are going to be a part of the language. So 0 times or more than 0 times, if you repeat this part, it is going to be in the language. The same for this example. This is a string from the language, right? 0, let me actually use another color for this one. So you have 0 and then 1, you iterate with 1 here, and then with a 0 you go to here, and with a 1 you go back here. Okay, so for this part, again, because this string here is going to iterate over some loops in the DFA, for example, this loop here, I can take this one, this part of the string, and repeat it as many times as I want, 0 or more than that. Still, the resulting strings are going to be in the language. The same as this example, that the loop that I'm actually checking is this part. I take this part of the string, which is corresponding to this part, this loop here, okay? And if I repeat it as many times as I want, still the resulting strings are going to be in the language. This is in fact a property for the regular languages. If you have a finite state, for the strings in the language, for the strings that are long enough, for all the strings that are long enough, if you take some part of the strings that actually go through some loop over some loop somewhere in the finite state, you can repeat that loop as many times as you want, including 0, and the resulting string is going to be in the language. This property is called pumping property. Okay, but notice that I mentioned all the strings in the language which are long enough. But how long these strings are going to be? I mean, by long enough, how much is going to be enough? For example, if I gave you a string like 0, the string 0 is going to be in the language, right? But can I take any part of this string and pump it as many times as I want and still the string is going to be in the language? No, right? If you can see, this string is going to actually traverse from Q1 and go to Q2. It is going to be in the language, but I can't take any part of the string to actually pump it, and then the result is going to be in the still in the string. For example, if I take this part, the 0 part, if I pump it only once, the result is going to be 0, 0, which is not in the language, right? So the strings of length 1 are not going to be long enough to go through a loop for me in this specific finite state. That length that I'm going to talk about is called, there is a name for that, and that is going to be called pumping length. We would say that all strings in the language can be pumped if they are at least as long as a certain spatial value. We call it a pumping length. What is that spatial value for this DFA? That spatial value is going to be 3. In fact, if you actually check this finite set, you will see that I need to have length 3 to make sure that all the strings in the language that has length 3 or more than 3, they definitely went through some loop in the DFA that I have here. And in general, the question is, for any DFA, if I have n number of states in the DFA, what will be the pumping length? Actually, for different DFAs, you may actually have different pumping length, but something that covers all of the DFAs of length n is going to be n. So the reason is, you can actually use the pigeonhole principle to prove that any DFA of with n states which accepts an infinite language is going to have pumping length n. It means that all the strings in the language that has length n or greater than n definitely will go through some loop in your DFA. And so the reason basically is that even if in the worst case you have a DFA like this one, with n number of states, and assume that this is going to be the accepting state, the last one, or actually anything. Somewhere here in the between, or for example, somewhere here or here or here, there should be a loop. If there is no loop in your DFA, it means that your language is not infinite. Okay, so we are talking about infinite languages. There should be a loop in your DFA. And if there is a loop in your DFA, if you are accepting a string of length n, definitely you are actually traversing n edges, right? N transitions. And because you have n number of nodes in your diagram, definitely you are going through at least one loop somewhere in your DFA. So that part can be pumped. The part that you are actually going through a loop, that part can be pumped. So we can prove that for any DFA of length, any DFA with n states, the pumping length is going to be n. Okay, so keep all this in mind. Now I am going to define the pumping lemma property more formally. Okay, so the pumping lemma, the formal representation of pumping lemma, we would say that if L is a regular language, then there is a number n, that pumping length that we discussed, where for all strings W in the language L, for all strings W in the language L, which are of length at least n, then we can rewrite W in, I mean, we can divide W to 3 parts, x, y, z, so that that y part is corresponding to a loop in the finite automaton for the language, and I wanted to actually force that y to be the first loop in the first loop in the language, or the first loop in the finite automaton. So those are going to be these constraints that I wrote here, that the length of y is going to be greater than or equal to 0. So that y is really corresponding to a loop. Okay, if y is 0, it means that it can be actually corresponding to no loop. So I at least need one character. And the other point is that I am forcing the length of xy to be less than or equal to n. By this constraint, I would make sure that y is going to be the first loop that I have seen. Okay, if I'm going to show it to you over the previous example that we had, for example, if you consider this one as the W, the first part is going to be x, this part is going to be y, and z actually basically is going to be equal to epsilon. We didn't have any constraint over z. The constraint that we had was over x and y, that the length of y is going to be greater than or equal to 1, and the length of xy is going to be greater than or equal to the pumping length, which is in this case is going to be 3. Remember, the pumping length for this automaton was 3. Or I can actually represent this one again, say that if it is going to be equal to W, again this part is going to be y, this part is going to be z, and x is going to be in fact epsilon. Or here this part is going to be x, this part is going to be y, and the rest of it is going to be z. Probably it would be better to use another color. Or here this part is going to be x, this part is going to be y, and this part is going to be z. Okay, we are basically just claiming that for any strings which is long enough, any string in the language which is long enough, I can divide that string to 3 parts, so that y is represented the loop, the first loop that we have in the finite automaton. Okay, so this loop that we found, the loop y, if you actually pump it any number of times that you want, if you pump it just once, if you pump it twice, 3 times, if you pump it k times in general, the result is going to be in the language. The result is going to be in the language in all of those cases. Okay, including when k is equal to 0, which the result is going to be just xz. Xz is also going to be in the language. This is the pumping lemma, pumping property for regular languages. This is a property that all regular languages has or the regular languages have. Okay, but if we have a language that we show it for that language that this property doesn't hold, if that language doesn't have this property, so that language is not going to be regular, right? This is exactly the technique that we are going to use to prove a language is not regular. The complete formal way to write the pumping lemma is going to be this one, that if L is regular language, then there exists some number n, the pumping length, that for all the strings of length n or greater than n, there will be some way to break it to 3 parts so that the part y is going to be corresponding to some loop, okay, and that will be the first loop in the string, that if I pump y for as many times as I want, the result is going to be in the language. As many times as I want, the result is going to be in the language. So this pumping lemma property cannot be enough to prove a language is regular. If the language is regular, definitely it's going to have this property. But if a language has this property, it doesn't mean that the language is regular. I have some examples for you that I will show you that the language is not regular, but it has this property, it has the pumping property. So unfortunately, pumping lemma cannot be used to prove a language is regular, but it can be used to prove a language is not regular. How we are going to use it? We are going to use it in a counterpositive way. If you can actually look at this this theorem that we wrote, this pumping lemma that we wrote, this part of it is going to be the hypothesis, and this part is going to be the conclusion. We are saying that if the hypothesis is true, then we can get the conclusion. If I'm going to use it in the counterpositive, I have to negate both the hypothesis and the conclusion. So it means that this box here should be negated and this part here should be negated. So I can write it as if not C, then not H. I'm going to actually just rewrite this theorem in the counterpositive way. So this box that you can see here is the negated part of the box here. How we are going to negate it? This is from the logic from discrete math. That all those there exist has been converted, all the there exists has been converted to for all, and all the for alls will be converted to there exist, and this part will be negated, and this part will be negated as well. So the result is going to be here. Okay, it is saying that for all number n, I can find some string in the language that the length of the string is going to be greater than or equal to n, that if you break it to 3 parts, all possible ways of breaking it, okay? It doesn't matter how you are breaking it, for it, any way that you find to break it, I can find some k that if I pump the middle part y for k times, the result is not going to be in the language. Okay, so if I show this, I can say that L is not going to be regular. At first, the counterpositive form of it might look a bit complicated, but if I'm actually showing it to you over some example, it will be more clear. The thing is, I am going to actually use pumping lemma in a form of a game. And all of these red parts are going to be actually the choice of your opponent, and all of the green parts are going to be my choice. So it is like your opponent is going to choose something, and based on that choice, you are going to do your best move and choose a good string, basically, that for all possible ways that someone is going to break it, you will show that it is possible um, to actually pump it for some specific number of times, and the result is not going to be in the language. So let me just go through some example. I think the best way to show it is using an example. Let's look at this example of palindrome strings. Assume L is going to be a set of all binary strings which are palindrome. Okay, so I wanted to actually prove that this language is not regular. By palindrome, it means that if you read the string from left to right or from the right to left, the result is going to be the same. So for example, if I have a string like 0, 0, it is going to be palindrome. If I have a string like 0, 1, 0, it is going to be palindrome. If I have a string like 1, 0, 1, it is palindrome. If a string like 0, 1, 1, 0, sorry, it is also palindrome. Let me actually find another example which is not palindrome. This is not going to be in the language. Okay, so basically if we wanted to rewrite this is going to be L is going to be all the strings in this form. Right, that WR is going to be the reverse of W. It means that if you read the string from left to right or right to left, you are reading it the same. Intuitively, it is clear that this is not regular, but intuition is not going to be enough for us. Okay, I'm going to show it to you using the pumping lemma. So just think about the pumping lemma as you wanted to prove it using a contradiction, a contrapositive way. So someone is going to claim the language is palindrome, okay? And you are the one who is going to prove that they are wrong and it is not. Sorry, the language is regular and you wanted to prove that the language is not regular. So if your opponent claiming the language is regular, it means that it is possible to create a finite automaton for it, right? And so if yes, you are asking them to give me a number. Okay, they are telling you that the number of states in the finite state for this language is going to be m. That is going to be the pumping length for us. Okay, so when they gave you m, based on m, I'm going to choose a string. What are the properties? What are the constraints over that string? The string should be of length greater than m. Okay, this is the only actually constraint over the string, but this is my choice that which string I'm going to use. I'm going to show you two different choices, that one of them is a good choice, the other one is a bad choice. So let's assume that W is going to be equal to W is going to be equal to this string, that I have whatever is m divided by 2 zeros, 1, 1, and m divided by 2 zeros at the end. So the length of this string is going to be definitely greater than or equal to m, and it is going to be in the language, right? This is palindrome. So if I use this actually a string as a choice, my opponent, this is my opponent's turn, they are going to divide it to 3 parts. Okay, so they are going to divide it to 3 parts, x, y, z. They are going to tell me that what is x, what is y, what is z. Why I am actually saying that your opponent is going to choose? Because when you are thinking that someone else is going to choose, you should consider all possible cases of this choice. The only constraint that you put is going to be this one. So the opponent can choose x to be equal to the 0 part, y to be equal to 1, so this is going to be x, this is going to be y, and this is going to be z. Okay, this is the choice of this is one possible choice of dividing w to 3 parts. But now you can see that if we take actually this choice, it is impossible for me to find a k that if I pump y for k times, the result wouldn't be in the language. You can see that if I pump y k times, the result is going to be still in the language. For example, if you pump it 0 times, the result will be something like this. If I pump it once, the result is something like this. If I pump it twice, the result is going to be if you pump it, I don't know, 3 times, the result is going to be in all of these cases, the resulting string is in the language. So basically I failed. I failed not because the language, not because it is not possible to show the language is not regular using pumping lemma. I failed because this choice is not a good string to prove that the language doesn't hold the pumping lemma property. So let me show you a better actual choice. I came back with a strong move. Now I am choosing w to be a string like this one. M number of zeros, 1, 1, and m number of zeros again. You can see that this is going to follow all the constraints. The string is in the language, the string is palindrome, and the length of the string is going to be greater than or equal to m. So now, if you divide, if your opponent in fact divide the w to 3 parts, they can actually divide it in any way that they want, right? But there is something. I have this constraint xy, the length of xy is going to be less than or equal to m, and the length of y is going to be greater than 1. Okay, so it is forcing your opponent that whatever is the choice of x, y, and z, definitely both x, y is going to be from the 0 m part of your string, right? Because the length is going to be less than or equal to m, so x, y should be chosen from this part. And the rest actually will be z, whatever it is. So it is telling me something. It is telling me that whatever is going to be y, y is going to be some zeros. Okay? So whatever is y is going to be some zeros, more than one number of zeros. It just tells me that if I pump, for example, if I pump only 2 times, so x, y, y and z, if I actually choose k equal to 0, the result is going to be this, right? So if x, y, z is equal to this string, then if you repeat y twice, y is going to be a couple of zeros, right? I don't know how many zeros. Maybe 1 0, maybe 2 0, maybe 3 0. It doesn't matter. It's going to be some zeros. The result is going to be whatever is the previous result. This is going to be plus some more zeros, then 1, and then another, I mean the rest of the string, right? So this is in fact going to be a string like this, and you see that this string is not palindrome. You have more zeros here than here. Okay, so I prove that there is a string like this, that if you take a part of it, which part that you want, this is going to be a loop. If there is a finite state for that, it is going to be corresponding to be a loop, right? Corresponding to a loop. And if you iterate over that loop, the result is going to be a string which is not in the language. So I prove that this is not going to be a regular language. We actually won. We showed that for the palindrome language, if someone claims it is regular, I can prove it otherwise. I can prove that if you are saying it is regular, it means that there is a DFA for that. If there is a DFA, give me the number of states. So that number of states is going to be m. I am actually giving you a string and telling you that it doesn't matter how you are going to create that DFA. A part of actually this string is going to be corresponding to a loop, some part here. And if we repeat that loop, the resulting string is not going to be palindrome. So it means that we cannot create a DFA for this language. So let me show you another example. Probably let me start with something simpler, then come back to this one. Remember this language from the this was actually the first example that we have seen about non-regular languages. N number of zeros followed by n number of 1. This is not regular, and I can prove it using pumping lemma. So assume that m is going to be the pumping length. Assume that someone claimed there is a DFA for this regular language of length m. Okay, this is not a regular language. I'm just assuming that someone is claiming it is regular, so there is a DFA with m states. Then you would actually say that if there is a finite state of with m states, your finite state is going to accept this string as well, right? It is a part of the language. If it is a part of the language, it means that there will be some loop here. Okay, you can divide this string to x, y, z, and there will be a loop in this part. So y is going to be some zeros. And if I just actually repeat that loop one more time, the result is going to be a string like this one. M plus r number of zeros, whatever is the length of that loop. M plus r number of zeros and followed that by m number of 1. Clearly, this is not in the language. Okay, so we prove that this language doesn't actually have the pumping property, so this language cannot be regular. Let me show you another example. for example, something like this one. A string with equal number of zeros and equal number of a string with has any equal number of zeros and ones. Again, this example was the second example that we have seen today. Right? It is not a regular language. I'm going to actually show it using pumping lemma. Assume someone is claiming it is regular. So there will be a DFA with m number of states. This will be the pumping length. I am going to choose a string, okay, a string in the language with length greater than or equal to m. My choice is this one. You can see that this is exactly the same choice as the previous actually example that I chose. It doesn't matter. It is going to work for me. Let me actually show you this example. If I chose this string, this is in the language, and the length of the string is greater than m. So if you run it over the DFA that you claim you have, right, this part is going to iterate over some loop. If I iterate over that loop one more time, the result is going to be a string which is not going to be in the language. So again, we showed that this language doesn't have the pumping property, so the language cannot be a regular language. Some notes, for example, if you choose a string like this one, this is going to be in the language, right? But this is not a good choice for us. Play with this one and see that this is not going to be a good choice for this language. Okay, so far we have seen a couple of examples that a language is not regular, and we prove it is not regular by showing the pumping property or pumping lemma doesn't hold for them. I'm going to show you another interesting example here. Think about the language L, which is all the strings of 0, that there is a specific property constraint about the length of the number of zeros. T is going to be a composite number. Okay, what does that mean? It means that T is not prime number. Okay, so for example, T can be 4, T can be 6, T can be 8, T can be 9, 10, 12, all non-prime numbers. Okay, I wanted to actually prove that this is going to be a not regular language. We wanted to actually see that what would happen to the pumping lemma property. Can we show it, show using pumping lemma that the language is not regular or no? So let's assume the pumping length is going to be n. Okay, then I have to choose a string. Let's just assume that the string that I am choosing is going to be something like 0, how many zeros? 2n number of zeros for some value of whatever is n. The string that I'm choosing is going to be 2n number of zeros. Okay, so actually, if this is the case, we are going to divide this string to 3 parts. Okay, and we have to prove that it doesn't matter how we are dividing the string to 3 parts under this constraint, we should prove that pumping lemma doesn't going to actually hold. Okay, so this is the choice of be careful. This is not your choice. You cannot say that, okay, choose y equal to be 1, 0. You should consider all possibilities. So y, someone can actually claim that y is going to be 2 zeros. This is going to follow all the constraint here, right? So this is following the constraint, and then what would happen? If you actually try to choose some value of k, that if I pump y for k times, the result shouldn't be in the language L. Unfortunately, with this choice of y, it doesn't matter how many times you pump y, the result is going to be in the language L, because this number is going to be a composite number, right? It doesn't matter if k is equal to 0, 1, 2, 3, whatever is the value of k, the result is going to be a composite number. This is not going to be a prime number. So again, you might actually just claim that, okay, this string is bad, choose something else. What you are going to choose? If you choose something like 3n, or for example, whatever you choose, it should be some composite number, right? It can't be a prime number. So if you choose this string, okay, the opponent can choose that, can tell you that y will be 3 zeros, for example. Again, you actually reach to the same issue. You cannot prove, you cannot find any k that the result is going to be, after you pump it k times, the result is not in the language. If you choose any number, actually a string, at the end the result is going to be, your opponent can find some string wise, can find some way to divide the string to 3 parts, so that if you pump it as many times as you want, still the pumping property is going to hold. So this is exactly an example of a language which is not regular. I can actually prove it that the language is not regular, but the pumping property does hold for this language. So remember at the beginning I told you the pumping property is a property for regular languages, but it doesn't mean that if a language has the pumping property, it means the language is regular. This is exactly an example for that. The language is not regular, but it has the pumping property. So how I can prove this language is not regular? I'm going to show, to actually prove it using the closure properties that we discussed last time. In fact, one thing that I wanted to actually, one more thing that I wanted to mention here is, if you have a language that for example, a language of, in this form again, that unlike this example, the language that is saying t is going to be composite, here I'm going to actually say that t is going to be prime. Let's call this language L prime. Okay, the language of some strings that the number of some zeros, each string is going to be a couple of zeros, that the number of zeros is a prime number. For example, so this language is going to be 2 zeros, all prime numbers, 3 zeros, 5 zeros, 7 zeros, and so on, all prime numbers. Okay, so this language is not regular. We can prove it using pumping lemma, and I'm skipping it because the complete proof is available in your textbook, so you can refer to that. But I'm going to use this to prove the language L is not prime. How I'm going to do it? So take this one as a fact, that this language L prime is not regular. The proof is available in your textbook. Read that. It is very interesting proof. Okay. So I am claiming that the language L prime is going to be the complement of language L. So why, here probably just one thing that I need to add is this sigma is going to be, the alphabet is going to be only symbol 0, nothing else. So in that case, definitely L prime that I have here is going to be all possible strings that you can create minus the language L that we are actually working on. Okay, and we know L prime is going to be, this is a fact, that the L prime is going to be a non-regular language. So definitely the complement of L is going to be L prime, right? And we know that, okay, and vice versa, the complement of L prime is going to be L. From the closure properties, we know that the regular languages are closed on their complement. So it means that if a language is regular, the complement of that is regular as well. So the complement of L is going to be L prime. If we are claiming L is regular, L prime should be regular. But L prime is not regular. We take this one as a fact that L prime is not regular, therefore L cannot be regular. This is an example of how we use the closure properties to prove a language is not regular. In some cases, we actually can use the closure properties to prove a language is regular as well. Okay, let me show you another example of using the closure properties to show something is not regular. Remember this example, all the binary strings that has equal number of zeros and ones. We just showed that this is not regular using pumping lemma, but I'm going to show it to you. I'm going to give you another proof using the closure properties. So in this proof, I'm going to use another language. Just think about L1, this language of n number of zeros followed by n number of 1. We just proved that this is not regular, and basically this is a very well-known language which is not regular. All these examples that I have shown you here, and there are more examples that I'm not covering. I just put the complete proof for your own read. All these examples that I gave you here, you can just take it as a fact. In your assignment, for example, if you wanted to prove something is not regular or something is regular, you can take any of these examples as a known fact. Okay, so I wanted to prove that this language is not regular. I know L1 is not regular. L1 to be n number of zeros followed by n number of 1. One thing that I know is this language is regular, right? We can basically, because I'm representing it using this language of a couple of zeros followed by a couple of ones. Arbitrary number of zeros followed by arbitrary number of ones. This is regular. The simple proof is that I'm showing it using a regular expression, so this is regular. And there is one fact about the language L1, L, and this regular language that I have here. Okay, L is going to be equal number of zeros and ones. L1 is this language, and L is just take this one as the final language that I have. The fact that we know about all of these three languages is that L1 is going to be equal to the intersection of L and all the strings in this form. Okay, L has this property that the number of zeros and ones is going to be equal, and this language has this property that it has a couple of zeros followed by a couple of ones. So if you take the intersection between these two languages, you get language L1. Okay? We know a fact about regular languages, that regular languages are closed on their intersection. So this is regular. If you are claiming L is also regular, then L1 should be regular. But L1 is not regular. So we have a contradiction here. Because L1 is not regular, L cannot be regular as well. That's it. That's the proof using closure properties. Here I am using a closure properties to prove that the language L is not regular. So that's almost all I wanted to actually explain in this topic of the pumping lemma. There are more examples here you can find. For example, all the strings over the all the strings in this form, that the number of zeros is going to be some complete square number. We can prove it using the pumping lemma. I have the complete proof here for you. Or another interesting example that I wrote for you is this one, that all the binary strings in this form, that a couple of zeros followed by a couple of ones, that we know the number of zeros is greater than the number of ones. Again, this is not regular, and we can prove it using pumping lemma. The complete proof for all of it, or for example, this example. I have all of these examples here, but I'm going to skip the proof in the video. If you have any question, contact me. So this video is going to cover section 4.2 from your textbook. Just read the textbook, read the slides, all the examples here, do the exercises, and contact me if you have any more questions. Thank you.